All right, guys. So we'll now move on to the last part of the lesson. So we are going to now discuss about toppling and sliding. Okay, so you do have some idea about this once again in M2. So we'll go through the whole thing again. So they say here you can determine whether a body will remain in equilibrium or if equilibrium will be broken by sliding or toppling. Okay, guys. So basically, you have your object. So they have kept the object on this inclined plane. So the question here is, okay, will it be in equilibrium or will it start sliding down the plane? Okay, will it start sliding down the plane? Or there's a third option. Third option is, will it topple? Like, will it completely fall over? Okay, so there are three possibilities. So we are going to explore the three possibilities. Is it going to stay in equilibrium, or is it going to slide down, or is it going to completely topple over? Right. So this is the you have to take this decision based on some calculations. Okay. So they say here, if a body rests in equilibrium on a rough inclined plane, obviously it should be rough, right, in order to be in equilibrium. So on a rough inclined plane, then the line of action of the weight of the body must pass through the face of the body which is in contact with the plane. Right, guys? So that's a really important thing. I think that this concept was discussed in M2 as well. So what they're trying to say here is, now if you compare these two diagrams, okay, if you compare these two diagrams, in the first one you can see that the weight, can you see the weight is acting vertically downwards. Now if you look at these two diagrams, you can clearly see a difference. In this case, okay, now, what are the forces you have here? Normally, you have the weight acting downwards. It's a rough plane. So you have the friction acting uh, along the plane should be upwards, right? Because the object is, on the verge of trying to move downwards, probably because of the weight. So the friction is acting upwards, right? So you have the weight, you have the friction, and there's another force here. So do you recall what that other force is? All right, guys. So the third force here that you need to remember is the normal reaction, right, guys? So the normal reaction is the third force, right? So you have the weight acting vertically downwards, friction opposing the direction that it's trying to move, and the friction and the normal reaction, okay, which is always acting perpendicular to the surface. Now over here, you need to also remember this particular rule. I hope you remember this. So this is the in an event. So anyway, just go through this one. So if a body is in equilibrium under the action of three forces, then the line of action of the three forces must intersect at a single point. So this is a rule that needs to be satisfied in order for an object to be in equilibrium under the action of three forces. Right. So the three forces or the line of action of the three forces definitely must intersect at a single point. Now, guys, over here you can see you have the friction acting upwards, weight is acting downwards, and you can see you can draw now normal reaction. You could draw it from anywhere, right? As long as it's perpendicular, that's fine. But the thing is, we need to draw this. There's a very specific point you can draw it from this point, because you can see this is the place where the two forces intersect. Can you see? So all three forces can intersect at this single point over here. Right, guys? Can you see? Right. So all the three forces, the normal reaction, the friction, and the weight. So they can intersect at a single point. So it is possible. For this in this particular diagram, there is a possibility that we have equilibrium. Okay. Equilibrium can be achieved. But look at the other diagram over here. Now, if you look at this particular diagram, you can see that you can see why there is a problem here, right? Can you see the weight is acting vertically downwards, and you can see, okay, friction is acting upward. So friction can only act, anywhere along this surface, right? So even though line of action doesn't mean, now the thing is I can draw, yeah, the friction of course we can have along this surface, so that's fine. Okay, the line of action, if you try to make it longer, you can see it's intersecting outside. Can you see? The intersection is kind of happening outside of the body. But the normal reaction is always acting along the surface of contact, right? So regardless of where you draw the normal reaction, I think you can see that it's not possible to intersect all the three forces at a single point, right? Is it possible to have all the normal reaction, friction, and the weight acting at a single point? You can see that it's not possible, right, guys? Can you see? Because the last place the normal reaction can act is over here. But they still don't intersect, because the normal reaction and the weight and the friction, all three are not intersecting together at a single point. So in this case, there is definitely, you don't have equilibrium here. So in such a situation, so this is a situation where you have toppling, because you can see the weight has jumped the range of the object, right? So that's what we read over here. Look, so if you read this again, if a body rests in equilibrium on a rough inclined plane, then the line of action of the weight of the body, see, the line of action of the weight of the body must pass through the face of the body which is in contact with the plane. Can you see? So over here, the face of the body which is in contact with the plane is this AB face. Can you see? AB is the face that's in contact. Now in the first diagram, the weight is passing through that particular face. Can you see? But in the second diagram, it's not passing through. So it has jumped that range. So definitely when you jump this particular range, the normal reaction and the weight and the friction, they cannot agree at a single point. This is a case where you have toppling here. So this is a case where the object will definitely topple, like, it will fall over. It will fall over. Right, guys? So this is an important diagram. All right, guys. So I discussed the rule about toppling. So now, when you talk about sliding, so I told you there's another thing where we have this sliding, right? So look at this. The body is on the point of sliding when F equals mu r. So F means, here the friction. Okay. So as long as obviously it has to be looking something like in diagram one. Okay. Because you cannot have the weight jumping outside the body of the plane, right? So in this case it's toppling, but in the diagram of like something like the first one, okay, so you can have sliding if the friction is equal to mu r. So this is an important one. Okay, let's go through these with examples so that you can understand better. But right now, let's just go through the conditions, and you will be able to understand this a lot better when we go through examples. Okay. And then this one, the body is on the point of toppling when the reaction acts at the point about which turning can take place. Guys, do you understand that statement? A body is on the point of toppling when the reaction acts at a point about which turning can take place. Now, if you look at this particular body, where can turning take place? So, guys, if you look at this body, turning can take place. Turning takes place at the end A or at the end B. You need to decide that. So if there is a toppling happening, the toppling will happen. Can it happen around B? You know that there's no way that it can topple around B, right? It's going to topple around A, right? The whole body will topple around A, right? That's the toppling point. So what they're saying here in this question is the body is on the point of toppling when the reaction acts at the point about which turning can take place. So if your reaction is acting at the very last point, so if your reaction acts like somewhere over here, so definitely that's happening here because the weight has jumped outside the body. Okay, so when your reaction is acting at at the point where the turning takes place, then definitely you have there will be the object is on the point of toppling, right? So that's what they're trying to say here. If the reaction acts at the point which toppling can take place, then your body is about to topple. All right, guys. So those are some important things that you need to do. Okay, so what we'll do is let's go through some examples to understand these concepts better. All right, guys. So we'll move on to exercise 60, question number 1. They say a uniform solid cylinder with base diameter 4 centimeters stands on a rough plane, inclined at 40 degrees to the horizontal. Given that the cylinder does not topple, find the maximum possible height of the cylinder. Okay, right. So let's get it done. Okay, what do we do here? First, let's draw the diagram. So you have an inclined plane, inclined at 40 degrees to the horizontal. And you have a cylinder that is resting on this plane. Right, guys? So this is the axis of the cylinder. All right. So now, so this is the cylinder. Okay. So now they're asking you, the question is, given that the cylinder does not topple, find the maximum possible height of the cylinder. All right, guys. So you can see that I'm now starting to mark all the forces. So I'm having friction definitely acting upward. So guys, in order to get the maximum possible height of the cylinder, like, the maximum height, okay, the thing here is you need to consider Okay, you need to consider. Okay, we are gonna kind of like create a right angle triangle here. At this point, we don't know this height. Okay, our task is to get this height. I think you need to realize that the taller this is, right? The taller this is, there's a chance of kind of like toppling over, right? Do you see that? Actually, the shorter the cylinder is, the more stable. The taller it is, the taller it gets. You do realize there's a good chance of it toppling, right? Because the weight. Now the weight of a cylinder acts exactly in the center, right? The weight of the cylinder acts exactly in the center, and they're asking you to find the maximum possible height. Do you see that? They are asking you to find what is the tallest that we can make this cylinder. Right, guys? So you need to realize that if the cylinder is actually short, okay, if the cylinder is actually very short, okay, then you really don't have much of an issue because the weight can directly go through the face of the object. Like you can see it's going through this, it doesn't jump outside the body. But you need to realize that the taller this object is, the taller the cylinder becomes, the taller this cylinder is, right? So when the weight is acting exactly in the middle, guys, can you see that it can jump out because the weight is acting exactly in the middle, and when it acts vertically down, you can see it's going to jump out, right? Because the taller it is, the center of mass acts exactly in the middle of the cylinder, and the vertically down, this weight can jump outside of this body. Can you see of this? This is the plane that. The place where the cylinder is touching the inclined plane. So if it jumps outside of that, you know that you are definitely toppling over, right? So in order to get the maximum height where it can still be in equilibrium, guys, you need to the hidden meaning in this question is like you need to consider this cylinder to be at the point of toppling. It's not toppling, but it's about to topple because that is the maximum height you can achieve. So at the maximum height you can possibly get for this cylinder, the weight is going to act at the last point. Can you see, guys? So if the weight is acting, can you see this? This is the special place. It needs to go through this very last point where it touches the inclined plane, because this is the last place where the inclined plane can touch where the inclined plane touches the cylinder, right? So let me name that point as A. I'll name this point as A. So if this is the AB, if I take the diameter as AB, so A is the last point that the weight can pass through. Right, guys? So you need to realize if the height is a little bit, even if it's a little bit higher, okay, if the height gets a little bigger than this, the weight will jump outside. All right, guys. So the maximum possible height means the maximum height that you can possibly get so that the weight can go through this very last point. Okay, because you need to realize the shorter the cylinder, the weight will go inside. The weight will not jump outside. The shorter it is, the weight will go inside. Right, guys? Can you see? But the taller it gets, the weight comes closer and closer to this point. And if you make it any more tall, this guy will jump outside. Okay, guys. So that's the important. And you can see here the normal reaction can pass through the very last point. Right, guys? So the three forces are still meeting. So it's possible to be in equilibrium, but this is the place where we call as where it's about to topple. So whenever they say it's about to topple, this is an instance where it's about to topple. So they've not told it to you directly, but you need to figure it out. When they say you to find the maximum possible height, yes, you need to consider the cylinder to be at the point of toppling. Okay, that's where you have the maximum possible height. Right, guys. So now it's simple geometry from this point onwards. So how does geometry work here? So this is the right angle triangle, 90 degree. If this is 40, you can see that this is a 50 degree, right? By geometry. So 90 degree, 40, this is a 50 degree. Vertically opposite angle, this is 50. Again, we have 90, and this is again a 40 degree. Can you see, guys? So this is the angle that I'm most interested in, because most of the time they would give the inclined plane angle as alpha and ask you to find alpha. So you need to realize that if this angle is alpha, that alpha it replicates over here. Okay, over here it's 40, 50. Since the angle is given, it's not much of an issue. But when they give you the angle in terms of alpha, the main thing you have to realize is this angle now, the one I'm coloring in yellow. highlighting in yellow. So this alpha, if I name this as alpha, alpha is coming back again over here. Inside the cylinder, you can see there's a right angle triangle, right? I have constructed. And then guys, you know that the center of mass acts exactly at half of the height. In a cylinder, you know that this is half the height, right guys? And you know that this length is the radius, right? You know that this particular half of AB, right? So the axis of the cylinder, I mean, the weight acts on the axis of the cylinder, and the height is exactly half the height, and this is the radius. All right, guys. All right, guys. So, okay. So I have the diagram set up now. So now it's time to find the height, right? So I think we know the base diameter 4 centimeter. If the diameter is 4 centimeter, it means the radius is 2 centimeter. All right, guys. So we are ready now. So let's apply sine cos tan to this right angle triangle, the one I'm shading in red. So we can go with tan 40, right, guys? Tan 40. Opposite over adjacent. Opposite over adjacent. Opposite is R, adjacent is H over 2. Right, guys? Opposite for the 40-degree, opposite is the R and adjacent is H over 2. So tan 40 equal opposite. The radius is 2 centimeters. Height H over 2 is unknown. We need to find H actually. So tan 40 into H over 2 equals to 2. Make H the subject. So the 2 goes up 2 times 2, 4 divided by tan 40, and make sure your calculator is in the degree mode. The calculator in the degree mode because the angle is in degree. Type this expression 4 divided by tan 40 degrees, and you get your and you get the maximum possible height of the cylinder. All right, guys. So the height is 4.77 centimeters. That's to correct it to 3SF, right? So write down the significance. Okay, always mention it. All right, guys. So we'll move on to another question now. Okay, so question number 4. A uniform solid right circular cone of mass m with base radius r and height 2r is placed with its circular plane base on a rough horizontal plane. So this is a rough plane, okay? A force P is applied to the vertex V of the cone at an angle 60 degrees above the horizontal as shown in the diagram. All right, guys. So we have an extra additional force acting over here. Okay, the cone begins to topple and to slide at the same time. So, guys, now I think you are quite familiar with the toppling story now, right? So, toppling is you realize that toppling is when I mean the object is now the thing is when you look at this particular diagram, you need to decide okay if it is going to topple, where is it about to topple? If it is going to topple, then where will it topple? Right? So you need to realize, guys. Now let me name the points. Okay, so I'll name this point as point A, and I'll name this as point B. So considering the force that you're pulling now from the vertex V, you're giving this extra external force and you're pulling it. So if you're pulling in this particular direction, think for a moment and think for a moment and ask yourself, where will this topple? Is it going to topple about the end A, or will this cone topple about the end B? So where will it topple? All right, guys. So you do need to realize where it's about to topple over. So I told you to think for a moment. So I hope you can see that if it's going to topple, if the object is going to topple, it's going to topple around B, right, guys? Because if you're pulling it in this direction, it's B. B is the point where the toppling is gonna happen, right? So then, if it is about now we'll talk about the toppling first, and then we'll go for the sliding. So if it is about to topple, what was the rule? The normal reaction will act on the point of toppling. So that's how it works. The normal reaction will definitely act at the point of toppling. So all you have to do here is your normal reaction. You should mark the normal reaction. You should mark the normal reaction at the point B. So this is the most important thing here, guys. Right? So you need to realize, I mean, you can't just mark the normal reaction randomly now. The normal reaction must be marked at point B because it's about to topple from B. Right, guys? Okay, what are the other forces we have? So you know that you have the weight, right? So your weight, it's a cone and you have axis of symmetry. So your weight will act vertically down. Your weight will act vertically downwards. And guys, your weight is going to act vertically downwards. Now here, don't try to make the forces intersect, right? Because we are not working now with three forces. If you realize, you have normal reaction, weight, you have the friction, and there is another external force, P. So don't try to, try to find a place where they all intersect. Okay. Right. So then it's under the action of more than three forces here. So normal reaction acting definitely at point B. Weight definitely acts vertically downwards from the center of mass. You have the force P here, and you have the friction. So guys, now they're talking about sliding here. So my next question to you is, if this object is gonna slide, okay, sliding means it's going to just move on this plane. I mean, it's going to move on this horizontal surface, right? So sliding can occur in two directions. Either you slide to the right side, or either you slide to the left side. So my question to you is, if this is going to slide, to which direction will it slide? Will it slide to the right, or will it slide to the left? According to this force. Now remember, it all depends on this force, the direction, because that's the external force you are giving. So according to this external force that you are giving, if there is a chance of sliding, will it slide to the right side, this one, the right side, okay? Or will it slide to the left side? I'm asking not the direction of friction, I'm asking the sliding direction. If the object is gonna move, slide, and go through, will it slide to the right, or will it slide to the left? So guys, I hope you thought of it for a moment. So you need to realize here that if you're pulling with this particular force, you need to realize even this P force, you can kind of like, resolve it. Like you can see that you can resolve this force P cos 60 to the right side, and P sine 60 upwards. Can you see? We can resolve it. So you can see that P cos 60 is the person who is pulling it to the right side. So there's a chance if it is sliding, this object will slide to the right side, not to the left, right? So the object will slide to the right if it is sliding. So guys, another thing is, I want to mark friction. So friction is always going to act in the direction opposing the direction that you're trying to move. So if the object is trying to move to the right, friction is going to act in the opposite direction. So you can mark friction in the opposite direction. So mark friction in this direction. All right, guys. So this is the force diagram. This is what you need to understand. The number one, the normal reaction is acting at the point B. That's really important. The weight acts vertically downwards from the center of mass of the cone, and the friction is acting to the left direction. So you need to mark all of these correctly. Right, guys? So that's it. So the cone, now they say the cone begins to topple and to slide at the same time. So toppling is taken care of. But if you recall, what did they say? If the object is about to slide, they said the friction is equal to mu var, right? I think I did give you that note at the beginning, right? A body is on the point of sliding when F equals mu var. Can you see, guys? So that's the condition that needs to be satisfied here. Right. So they're asking you here. So basically that means this friction that you have over here should be equal to mu r. Right, guys? Do you agree with me? Because if it is, now the question says it's on the point of sliding. So that means this friction must be equal to mu r. Okay, because they say it's about to slide. Okay, I'm using F equal mu r because they say that it's going to slide. So they're asking you, find the magnitude of the force P in terms of capital M. Okay, so I think I should mark the weight not as W. Okay, so mass capital M, so which means weight is mg. Let's mark weight as mg. Weight is mg. Okay, so you're supposed to find the force P in terms of M. So guys, this is the normal M1, M2 question. So there are three things to do in these kinds of equilibrium questions. What are they? You can consider vertical equilibrium, or you can consider horizontal equilibrium, or you can consider moment and make the moments, take moments around any point and make it equal to 0. So these are the three things that you can do over here, guys. So either you can consider vertical equilibrium, horizontal equilibrium, or moment. Okay. So how do we find P in terms of M? So which is the best method to go with? All right, guys. So I think I'll just quickly go through this. I think you might be confused probably. So if I go back over here, guys. So this was the condition to slide. Okay. Just to make things clear. Okay. So if the body is on the point of sliding when F equal mu r, this is the condition to slide. The second point I told you, this is the condition to topple. All right, guys. So this diagram over here is for the toppling. I think some of you might be wondering about this diagram, right? So what is this diagram and what's going on here? Why is the norm R marked vertically like this? But actually, guys, if you read the description they've given over here, they've said that they're talking here about the total reaction that consists of normal reaction and friction force. Okay, guys. So I really do. I'm not. I really don't encourage you to try to pursue in this method because what they've done here is they've taken R as a combination of the normal reaction and the friction, both normal reaction and friction. They've taken the resultant of the normal reaction and friction, and that is the force that's acting vertically upwards, opposing the way to keep the equilibrium. All right, guys. So uh, it's better that you don't go with that diagram, but these diagrams are much more, a lot more helpful. You have the friction here, right? Yeah. So these diagrams are better. Work with these diagrams, okay? So what I wanted to realize is for sliding, F equal mu r, and for toppling, the reaction takes place, the reaction will be at the point where the toppling can happen, okay? So that's the condition. Always go with those conditions. All right, guys, I hope it's clear. All right, guys. Okay, so coming back to the question, as I told you, so these are the, I've marked all these forces to satisfy the conditions of toppling and sliding because they have told in the question, toppling and sliding are happening both together at the same time. Now, it's in this question, okay, according to this question. All right, so according to that this question, I've marked all the forces with respect to these requirements. All right, so now it's time to solve for P. Okay, so as I told you, you have three options here. So object is still on the edge of equilibrium. So you can have vertical equilibrium, horizontal equilibrium, or moment. Right, guys? So I think out of all the three options, the best option here is to consider moment. Right? So why is moment the best option? For example, if you consider moments around B, okay, if you consider moments about B, guys, you can see that there are many advantages of taking moments around B, right? Because number one, the normal reaction passes through B, so you don't have to deal with normal reaction. And also, you can see the line of action of friction. The line of action of friction also passes through B. That gives you another advantage. You don't need to even consider friction for the moment. So when you take moments around B, there are several advantages. Number one, P is not considered. And number two, the friction is not considered. Okay, so then the only forces that will give moments are the mg, weight, and guys, the P cos 60 and the P sin 60. So we'll work with P cos 60 and P sin 60. That will be easier, right, guys? All right, so this is simple M2 moments. All right, so let's mark the moments around B. So moments around B. So what's moment? Moment is force into perpendicular distance, and you need to decide whether the moment is clockwise or anti-clockwise. Right. Okay. So you keep you around B. So you keep your finger around B and mg. Okay. So mg is gonna give a clockwise moment to anti-clockwise moment, guys, around B. Okay. So you can see if you keep your if you so let me show it to you. Okay. Let me show it to you from the compass. Okay, so these are stuff that you are supposed to be familiar with. So let me keep. So you keep your the compass point, or you keep your finger around B, right? And then you keep. Then you keep the. You keep this perpendicular to the force that you are trying to measure. So we are going with mg. So I keep it perpendicular to mg, and you can see mg is pulling this down. So if you pull the compass in that direction, you can see you're pulling it downward in the downward direction. That is you can see that this is a anti-clockwise moment. Can you see? That's an anti-clockwise moment. So therefore, so I've considered clockwise as positive. Okay, you can consider clockwise or anti-clockwise, anything you wish. So I've taken clockwise as positive. Therefore, mg is negative. It's an anti-clockwise moment. So minus mg into what's the perpendicular distance, guys? The perpendicular distance between mg and B is r. So it's simple as that, right? So force into distance. And you have to give the plus or minus, depending on the direction of the moment. Okay. All right, guys. So the next one is P cos 60. So if you want to get the moment of P cos 60 around B, you need to keep the placement should be that the compass or your finger should be the direction should be perpendicular to P cos 60. Now P cos 60 is horizontal, so you can see I'm keeping this vertical. So I'm keeping it vertical, and now you need to pull this particular the finger. You have to pull it in the direction of P cos 60. So P cos 60 is pulling it to the right. So when I'm pulling this to the right, can you see it creates a clockwise moment? Can you see it creates a clockwise moment? P cos 60 creates a clockwise moment around B. So if it's a clockwise moment, that's plus P cos 60. And guys, what's the perpendicular distance? The perpendicular distance between P cos 60 and B. So guys, you can see this is the perpendicular distance. Can you see the red color distance? This is the perpendicular distance, which is 2r. Right, guys? So perpendicular distance between P cos 60 and B is 2r. So P cos 60 into 2r. All right, guys? Okay. And then the next one. Okay, so how do you get the moment around P sine 60? So P sine 60 also gives the moment, right? So what you can do here is make the line of action of P sine 60 longer. Okay, so this is the line of action of P sine 60. Let me write P sine 60. So with green color, I'm just marking the line of action. Okay. And then what you can do is, so now I can keep the compass perpendicular to the direction. Can you see P sine 60 is having this upward movement? Can you see, guys? P sine 60 is having the upward movement. Okay, so I drive the line of action so that I can keep my finger, perpendicular to the line of action. It needs to be perpendicular to the line of action. And then you start pulling, so it's in the upward direction. So when I pull with in the upward direction, I can see again it's a clockwise moment. So P sine 60 also gives a clockwise moment. So it's again plus, because it's clockwise. I'm going to give plus P sine 60 into the perpendicular distance. Guys, perpendicular distance between the line of action and B. So perpendicular distance between the line of action and B is this guy, right? Can you see? This green color line and point B, the perpendicular distance is R. Right, guys? Do you understand? So that's it. These are the three forces, right? These are the only three forces that gives you moment, because friction, line of action of friction passes through B, it doesn't give a moment. Normal reaction passes through B, it doesn't give a moment. Only P sine 60, P cos 60 and mg gives you moment. So that the sum of moments must be equal to 0. All right, guys. So it's in equilibrium. Okay. So then you can now solve this particular equation and get P in terms of M. Okay, it's P in terms of M. P cos 60 into 2R mg into R cancels. P cos 60 into 2R. So P cos 60 is cos 60 is half, right? P sine 60 is root 3 over 2. So we can P plus root 3 over 2P equals mg. So you multiply the whole equation by 2. 2P plus root 3P equals 2mg. Right, guys? Taking P out, 2 plus root 3. And then making P the subject. So you have 2mg over 2 plus root 3. So this is the force P in terms of mg, in terms of m and g. All right, guys. Okay. So remember we are working with limiting equilibrium here. Okay, beginning to about to topple and about to slide. Right. So it's beginning. So considering limiting equilibrium, we do this sum. Part A is done. Part B. calculate the value of the coefficient of friction. They want you to find mu. Right, guys? Obviously, now to find mu, let's go with the other two options. So we have vertical equilibrium uh, and we have horizontal equilibrium. So we'll try to go with we'll go with horizontal equilibrium. So if you consider the forces that are acting horizontally, you can see horizontally we have P cos 60. So I'm going to consider horizontal equilibrium. So horizontal equilibrium, you have P cos 60, which is acting to the right, and that should be equal to the F, the mu R. Can you guys see? So it's equal to F, and we add all the mu R value. P cos 60 equals mu R. So P value is known. We just found the P value, right? In part A, we found the P value, but you can see we still have another unknown. We still don't know the normal reaction. R. R is unknown. So guys, in order to get R, we would consider vertical equilibrium. Let's consider vertical equilibrium. So when you consider vertical equilibrium, you can see I have upwards P sine 60. P sine 60 acting upwards, and what are the forces acting? And we have normal reaction acting upwards plus R, right, guys? P sine 60 acting up, normal reaction acting up, and then you have the weight mg acting downwards equals mg, right, guys? So from here you can make R the subject, R equals mg minus P sine 60. Can you see, guys? Right. So then all you have to do is to substitute back that value of R here. So let's substitute the R value. P cos 60 equals mu times normal reaction answer you found is mg minus P sine 60. Are you with me, guys? So make mu the subject. So when you make mu the subject, you get P cos 60 divided by mg minus P sine 60. Shall we substitute the P value? P is, so I'm going to substitute the P value here, okay? This P and this P. So P is 2 mg over 2 plus root 3 times cos 60. Mg minus P is again 2 mg over 2 plus root 3 times sine 60. All right, guys, can you see? Try to replace the P value in all the places. You can see there are three terms. Can you see there are three terms? First, second, and third. There are three terms. What you can do is you can take mg out from all the terms. I hope you guys can see that mg is common to both the numerator and the denominator. Capital MG. So you can remove it. Get rid of the mg. Mg is common to all of them. Now remember here, mg cuts off doesn't mean it becomes 0. It's 1 here. Okay, there will be a 1 remaining. So now you can get mu. It's a matter of typing it in the cal, right? 2 over 2 plus root 3 times cos 60 divide by, so I think your calculators can handle this quite easily. 1 minus 2 over 2 plus root 3 times sine 60. So give this expression in the cal and you can easily get the mu value. All right, guys. I think rather than, I think I did not simplify much enough in the previous step for R. So actually, you can see I've done the simplification here. That makes things a lot easier. Actually, this is a little bit more hard. Let me, let me, instead of going in this manner, okay, let's try a little bit better method. So you can see what I've done here is I've actually substituted the P value. Now, I did not, previously, I just kept the R like this and substituted it over here, right? But you can actually input the P value, 2 mg over 2 plus root 3 times sine 60. The simplification is not that hard, right? Because sine 60 is root 3 over 2 and the two numerator and denominator can cancel out. And then you have root 3 mg over 2 plus root 3. So you can go for the common denominator. This is the common denominator of these two guys are 2 plus root 3. So this mg multiplies with the 2 plus root 3 minus here you have root 3 mg. So when you open the bracket 2 mg plus root 3 mg and here you have minus root 3 mg, the root 3 mg is cancelled out. and R is equal to mg over 2 plus root 3. Can you see, guys? So that makes things really easy. And now you can substitute that to P cos 60 equals mu R. So P value, I think you can see P and R values are matching. Can you see? P is 2 plus root 3 into cos 60 equals mu times R is also 2mg over 2 plus root 3. So I can clearly see that these two terms can cancel out each other. They can divide, right? So they can divide because 2mg cancels out, 2 plus root 3, 2 plus root 3 can cancel out when they're dividing and, taking stuff to the other side. You can see that it goes as a reciprocal and it nicely cancels out with each other. So you're remaining with mu equals to cos 60. And cos 60 is half. So guys, this is your mu value, right? So I hope you can understand how to do a question. So I've tried to explain to you all the full mechanism of, what's going on here. All right. All right, guys. So next I'll move on to question number 10. A uniform solid cylinder of mass 200 grams, right? Be careful here. It's mass 200 grams, which means the mass is 0.2 kilograms, right? We don't work with grams, okay? I mean, be careful that you don't think of this as 200 G. If it was weight, then we can consider it as 200 G. But since it's mass, you should understand it's 200 grams here. Okay, so that means it's 0.2 kilograms and weight will be 0.2 g. Okay. Okay, so of mass 0.2 kilogram, height 4 centimeter and radius 3 centimeter, rests with its circular base on a plane. The plane makes an angle alpha with the horizontal where tan alpha is 3 over 4. That's given to us. Okay. The coefficient of friction is 6 over 17. Mu is also given to you. Okay, let's mark it up. Tan alpha 3 over 4. Basically, guys, when they give you tan alpha, you should immediately get these two values as well. Get the sine alpha and cos alpha. That will be useful. So sine alpha will be tan alpha opposite over adjacent, right? So according to Pythagoras, so this side will be 5. Sine alpha opposite over hypotenuse and cos adjacent over hypotenuse. So these are three ratios. So I got the three ratios. And coefficient of friction mu is 6 over 17. A horizontal force P is applied to the highest point of the cylinder as shown in the diagram. Find the value of P which will cause the cylinder to topple above the highest point of the base. So guys, do you see what they are saying? So they are saying they are pulling this about B and because of this particular force, they are saying it's going to cause the cylinder to topple about the highest point. Can you see? It's not toppling about this point. Basically, because the force is pulling to the right direction, the cylinder is now going to topple about the highest point. So guys, the toppling is going to happen over here. Can you all understand? So since they're talking about toppling, so what was the rule? If your object is about to topple, then the normal reaction will act about the point of toppling. So you can immediately mark your normal reaction. So this is the normal reaction, right, guys? Right? I hope you guys get what's going on here. So this is the point of toppling. So this is the point of toppling. Tan alpha 3 over 4, coefficient of friction. Okay. So find the value of P that will which will cause the cylinder to topple above the highest point of the base. Okay. So guys, let's mark all the other forces. I'm trying to mark the axis of symmetry of the cylinder. All right, guys. So weight will act in the middle. That's 0.2 G. And you'll have normal reaction is acting over here. And guys, the coefficient of friction, so that means you do have friction here. But however, now they're asking in order to mark the direction of friction, you need to know whether it's about to move up or down. So they're not saying any such thing. So actually over here, the friction is not going to make much of an effect. Why? because you are trying to find the value of P. And if you're trying to find the value of P, so let me just mark friction. Okay, but you can see since I'm marking friction on this particular plane, I'm going to consider moments. I'm going to consider moments about the point of toppling. So if I consider moments about the point of toppling, guys, the friction won't, it won't affect us now. Okay, because the line of action of friction will pass through this particular point. So I'm going to consider moments, and we are going to consider moments to try to find the value of P. All right. So the direction of friction won't make an impact whether it's moving up or down. So probably it might try to slide up. So anyway, so I'll mark friction. So probably there's a chance that if it's trying to depending on the force that you're pulling here. Okay. So anyway, friction makes no impact. Okay. So you only have the weight and the normal reaction. All right. So guys, the complicated part here is now how to get moments. How to get moments around this about this particular point. I'll name it as point B. Okay. So this is point A and this is point B. A and B. I want to get moments around point B, and I want to find I want to find the value of P. All right, guys. So when you take moments around B, one thing that you are immediately clear is normal reaction will not make an impact because the line of action of normal reaction passes through B, and friction also will not make an impact. So the only two forces to consider here are the P and the point 2G. So those are the only two forces that you need to consider. All right, guys. So now the challenge is how to get the distances and how to do the resolving here. Okay, so let's start on that. All right, guys. So to get moments, we need to kind of resolve these forces. Okay, so at this point, you can see there are, first, let's consider point 2G. Okay, I'm going to consider point 2G first. And guys, when you work with point 2G, you can see if I try to go with force into distance, now here force is the point 2G and distance, I need the perpendicular distance to B. The perpendicular distance to B is like something like this, right? Can you see? And it's kind of like, it's not possible to find this distance like immediately. We have no way of finding such a distance, right, guys? So what you need to do here is we need to resolve. Okay, we need to resolve. Guys, I hope you understand that why I used alpha here, right? So do you realize why I used alpha here? So this was a concept I was explaining at the very beginning, right? So this alpha over here, 90, this is 90 minus alpha, vertically opposite angle, 90 minus alpha here, 90, and this should be the alpha, right? I think I explained this with the example with the 40 degrees. Do you recall the very first question with 40 degrees? I showed you how the 40 comes over here. So you have that same concept over here as well. Okay, guys. So to do this, we will not work with point 2G, but we will work with the resolved forces. Guys, look what I'm talking about. I'm going to resolve this point 2G. Look at the two directions. Can you see? So I can work with these two directions. So this is going to be point 2G sine alpha. And this is going to be point 2G cos alpha. Can you see, guys? So I'm not going to work with 0.2G anymore. I'm going to work with these two. And you can see there's a big advantage in working with these two, right? Because 0.2G cos alpha is going through the axis of the cylinder. And when I go with that, you can see I can actually get the distance now. And even 0.2G sine alpha, this is exactly the middle of the cylinder. Can you see it passes through exactly the middle? So I can get the distance really easily. Okay, so that's the reason why I'm going for the resolving here. So you must do the resolving to make things easier here. Especially you can calculate the distances easily now. All right, guys. So you can see that solves a major problem. Okay, so if I'm going to consider moments around the point B. I'll consider clockwise as positive. So take considering around B. All right, guys, considering around B. Uh, so how are the distances coming? I'm going to keep this around B, and I'm focused on 0.2G cos alpha. So 0.2G cos alpha, you can see it's pulling down, right? So it's giving a anti-clockwise moment around B. Can you see 0.2G cos alpha gives an anti-clockwise moment around B? Do you guys agree with me? So anti-clockwise means it's negative 0.2G cos alpha into what's the distance, guys? What's the perpendicular distance? 0.2G cos alpha, the perpendicular distance is directly the radius. Can you see? So that's what makes this really easy. So the radius is 3 centimeters, guys. Right? I hope you understand it. This is the key thing here, the key feature here. 0.2g cos alpha has the radius is the perpendicular distance between 0.2g cos alpha and b. That's what makes it easier. All right, guys. And what about 0.2g sin alpha? What is the what is the direction and what's the distance? So I'm going to make the line of action longer. You can see I'm making the line of action longer so that I can keep my compass point perpendicular. Okay, so guys, can you see what I'm doing over here? I'm keeping the compass point, and you can see this goes in this particular direction, right? Can you see? So then I keep the point perpendicular to the line of action, and then I pull along the directions of the arrow. So when I pull along the direction of the arrow, 0.2g sine alpha is also giving me an anticlockwise moment. Can you see? 0.2g sine alpha also gives me an anticlockwise moment. So that's going to be again anticlockwise means negative 0.2g sine alpha. And guys, what about the perpendicular distance? What about the perpendicular distance? Guys, the perpendicular distance between B and 0.2g sine alpha is this, right? It's this distance. Can you see? So this is B and this is the line of action of 0.2g sine alpha. The perpendicular distance is, can you see? So this is exactly going through the middle of the cylinder. So this is the height of the cylinder is 4, which means this particular distance is 2 centimeters. Can you see the advantage? So the distance is just 2 centimeters. The perpendicular distance between 0.2g sine alpha and B. Right, guys? Can you understand? So it makes things really simple when you do this resolving. All right, so I'm done with resolving the weight. Okay, and I'm done with the moments about the weight. But now we had to go for the other force. Who is the other force? So now I had to work with P. Okay, so now I have to work with P. So how do I work with P? You can see again, let me, I'm trying to erase all this. Okay, sorry, this was into 2, right? Okay. Right, guys. So now we'll work with P. Okay, so when you're working with P again, I want to consider moments around B, okay, and the moment produced by P. But again, you can see that there are some difficulties here. Can you see the difficulties? The thing is, when you consider around B and considering moments, I think one of the main difficulties here is to get the perpendicular distance. Can you see the perpendicular distance is this? And it's quite looking at this diagram, it's really it's kind of challenging to get that perpendicular distance, right, guys? Okay, you can do some trigonometry here though. There is a possibility. So I'll show you the resolving method, which I think is the easiest. Okay, or else you can consider a right angle triangle over here, consider angle alpha and actually try to do something as well. But over here, I'll show you the method that is the best working. So what you can do is, you can see I'm drawing this line. Can you see this particular line that continues the line of the object? Guys, I hope you can see that this angle is also alpha. Can you see that this angle is also alpha? Right? Can you see? Because P, now if you consider this from, from this point of view, you can see P is horizontal. And the line, the green line is, it's continuing along the slope of the object. Can you see now? If you consider over here, this is the horizontal and here the alpha. So this is the slope of the plane. Can you guys see that the cylinder is also having the same? The cylinder is parallel, right? Can you see, guys? These lines are parallel. Can you see, guys? So you can see that this alpha is actually coming over here. So that's one of the main things you need to understand. And now we can easily resolve P as well, right? So now you can easily resolve P and you can get to this side. So this is gonna be P cos alpha, right guys? And then you have P sin alpha acting down. So this is P cos alpha. This is P sin alpha. Can you see, guys? And again, the advantage here is P sin alpha passes through B. If P sin alpha passes through B, then you don't have to consider moments around about P sin alpha. P sin alpha will not give you any moment because the line of action passes through B. So you only have to consider moments with P cos alpha. Right, guys? And then let's consider moments about P cos alpha. You can see working with P cos alpha is easier. Why? Because it's easy to get the distance. It's really simple to get the distance. You can see the distance is directly 4 centimeters, right? So it's really easy to get the distance. So keeping the compass point around B and keeping it perpendicular to P cos alpha. And when I pull it in the direction of P cos alpha to the right, you can see it's giving a clockwise moment. So P cos alpha gives a clockwise moment. So plus P cos alpha into what's the perpendicular distance, guys? The perpendicular distance between B and P cos alpha is the height of the cylinder. That's directly 4. That's it, guys. P sine alpha doesn't give us any moment. Normal reaction friction doesn't give us any moment. So this is equal to 0. So you can see that this is really, I mean, it gets really simple if you do the resolving correctly. All right, guys. So now it's just a matter of making P the subject. So P cos alpha times 4P cos alpha equals the minus terms. I'll take them to the other side. Minus 0.2 G cos alpha into 3 plus 0.2 G sine alpha into 2. So 4 times P cos alpha. You can substitute the values, right? Cos alpha, I mean, we have the values here. 4 P cos alpha 4 over 5 equals 0.2 G cos alpha 4 over 5 into 3 plus 0.2 G sine alpha 3 over 5 into 2. Right, guys, make P the subject now. So it's going to be 5 over 16 times this whole thing. So get the P value, right? Can you see? 4 times 4, 16 over 5. When I take it to the other side, it becomes 5 over 16 of this entire term. And you can, type this in the cal and get the answer. G value, you can use it as 9.8. So if you use G as 9.8, make sure you give your answer to 2SF or 3SF. So let's get the answer. So guys, you can try to get your answer maybe in terms of G. Okay, sometimes they'll ask you to get your answer in terms of G. In that case, don't type the G, just type the other expressions. G is common to everyone, right? You can take the G out and maybe you can give your answer in terms of G as well. Okay, so because G is common, I'll just take it out. Okay, it was common to both the terms. I took it out. So you type all of this in the cal and just write it with G. So that's going to be 9 over 40. 9 over 40 G, right? Newton. If you use G as 9.8, then make sure you give it corrected to 2SF or 3SF. All right. All right, guys. So we'll move on to part B. Find the value of P, which would cause a cylinder to slide up the plane. So now they're talking about sliding. So guys, when you're talking about sliding up the plane, so we can work with this force diagram, right? Normal reaction is always anyway acting perpendicular to the plane in the upward direction. So now what I'll be considering is vertical and horizontal equilibrium, or rather I'll be considering equilibrium along the plane and equilibrium perpendicular to the plane. That is easier, right? I'm not going to again resolve and make it to the standard XY direction. That's going to be a lot of work. So rather I have all the forces actually resolved in the directions that I want. Can you see? Normal reaction, 0.2 G cos alpha, P sine alpha, they are all acting perpendicular to the plane, right? And P cos alpha, 0.2 G sine alpha, they are acting in the direction parallel to the plane. So that's good. So I can consider forces parallel and perpendicular to the plane now. So they're asking you to find the value of P that would cause a cylinder to slide up the plane. So what's the requirement to slide? In order to slide, the requirement is that F should be equal to mu r. That's it. If F is equal to mu r, then that means we are talking about sliding. So all you got to do now is take the forces and make them and equate them. So how do you equate? So if you consider, I think we'll have to first go perpendicular to the plane. First go perpendicular to the plane. Perpendicular to the plane, upwards you have normal reaction. Right, guys? Now remember the 0.2G, these P, these guys are not there, right? Because you resolve them means that they are no longer, we don't need to work with these guys anymore, right? Because I've resolved them. So only work with the resolved forces. Make sure the force diagram is complete though. Now you can see my force diagram is complete because I've marked all the forces. I mean, every single force that I've resolved is fully shown. Now P cos alpha, P sine alpha is also shown here very clearly. Right, guys? Can you see? Okay, so I can see normal reaction is acting upwards, 0.2 G cos alpha is acting downwards, and P sine alpha is acting downward. So normal reaction must be equal to 0.2 g cos alpha plus the P sine alpha. Can you see guys that these are the vertical forces? R is acting up, 0.2 g cos alpha, and P sine alpha is acting down. Do you guys agree with me? And guys, we can we get the R value? Yes, right? I think we know everyone. 0.2 g cos alpha is 4 over 5. P is 9 over 40. G sine alpha is 3 over 5. Guys, let's get the answer in terms of G. I think that would be easier. So don't input the G value in the cal. You give in the cal 0.2 into 4 over 5 plus 9 over 40 into 3 over 5. And then we'll put G at the end. So what is the R value? Guys, so sorry about this. This is wrong, right? This is wrong. Why is this wrong? It's wrong because you're supposed to find the value of P that would cause a cylinder to slide up. So I can't use this P value. This is the P value. The P value we found in part A is the P value that would cause the cylinder to topple. So I can't use that P value here. Plus the question is asking me to find the P value that would make the cylinder slide up the plane. So P has to be treated as an unknown. All right, guys. So sorry about that. So this is wrong. Okay, so let's cut that. Okay, so this is the equation is correct though. Okay, the equation is correct though. Okay, now you need to realize even though the normal reaction might not act at the point B, even if it acts at another point inside, it's still acting perpendicular upward. So it does not make any impact on this equation. Okay, it will not make an impact. So let's consider. So there are two unknowns now. Normal reaction is unknown, P is unknown. Can you see? There are two unknowns. So let's now consider parallel to the plane. Consider forces parallel to the plane. So when you consider the forces parallel to the plane, guys, what are the forces we have? We have P cos alpha. P cos alpha acting along the plane upwards. And what else do we have? We have 0.2 G and F, right? 0.2 G and F acting to the opposite direction. Parallel to the plane but downwards. 0.2 G sine alpha plus F. And you know, if you're on the point of sliding, F should be equal to mu R. F should be equal to mu R. So you input mu R here. Can you see, guys? So it's a pair of simultaneous equations. Two unknowns. P and R are the two unknowns. Here mu value is given, guys. Can you see? Coefficient of friction. Mu is 6 over 17. It's given in the question. Can you see? Coefficient of friction 6 over 17. So you have a pair of simultaneous equations that you need to solve. All right, guys. So we have to solve these two equations and get the answer. Okay, let me remove this. Let's try to simplify this a little bit more. Actually, what we can do is the easiest thing we could do here is substitute the R value directly, right? That would be that would give us that would be an advantage. Substitute the R value directly here and make P the subject. All right, guys, can you see what I'm talking about? So P cos alpha equals 0.2 G sine alpha plus 6 over 17 into normal reaction is 0.2 G cos alpha plus P sine alpha. All right, guys. Let's open the bracket and take all the P terms to one side. 0.2 G sine alpha plus 6 over 17 into 0.2 G cos alpha. You have to open the bracket with 6 over 17, right? Plus 6 over 17 into P sine alpha. Can you see? I expand the bracket with the 6 over 17 with both the terms. And then you take the P terms to one side. These two are the P terms. So you take them to one side. And you have here P cos alpha minus 6 over 17. P sine alpha equals 0.2 G sine alpha plus 6 over 17 into 0.2 G cos alpha. Take P out. You have the sine alpha cos alpha value, so you can substitute them, right, guys? Shall we substitute them to make things easier? So cos alpha was 4 over 5, sine alpha is 3 over 5. Maybe you don't have to give the G value. Cos alpha is 4 over 5, right? Cos alpha is 4 over 5. Yeah. So you can input the G at the very end. So P equals 0.2 into 3 over 5 plus 6 over 17 into 0.2 into 4 over 5. I've taken the G out, okay? Divided by 4 over 5 minus 6 over 17 into 3 over 5. So you can have this fraction entire in the cal and it will do it in the correct order of operation, right? Multiplication will be done first and it will do it in the correct order, right? So input the value and you can get the P answer in terms of G. All right, guys. So it's 3 over 10G. Can you all see? So P is 3 over 10G. That's done. That's the P value that will cause the cylinder to slide up the plane. And then guys, in part 3, they ask for 1 mark, show that the cylinder topples before it slides. All right. So now you have to show that it's going to topple before it actually goes to slide. How do you show that? It's actually quite simple, right? It's just 1 mark. The thing is, you found 2 P values here. In part A, you found the P value that causes the cylinder to topple. And in part B, you found the P value that is going to make the cylinder to slide. So let's compare the 2 P values. Okay. In part A, to topple, what was the P value? To topple, the P value was 9 over 40G. Can I have the numerical value? Like, give 9 over 40 into 9.8. Get the value here, guys. So what's the, I want the values here. To slide, our P value was 3 over 10G. You have to compare them. Either you can make a common denominator here or just get the numerical value. Anything is fine. You can make here out of 40 and see which one is bigger.
Yeah, teacher, even I get the same.
Okay. So guys, here 9 over 40G, here 3 over 10 is actually 12 over 40, right? So you can quite clearly see that this is larger. The 3 over 10 is larger. These are the numerical values. So guys, so that makes things very clear, right? So you can write here 3 over 10G is greater than 9 over 40G. Which means what? Now the thing is, before you reach 3 over 10, you first go through 9 over 40, right guys? So before you reach 2.94, when you are giving the P value, P is an external force that you are giving. So before reaching 2.94, you pass through 2.21. And the moment you go through 2.21, the cylinder will topple. Therefore, you don't have to go, you will not go to the phase of sliding. You will end the phase from here. Can you understand? So therefore, the cylinder will what? What's going to happen first? The cylinder will topple, right? The cylinder will topple before it slides. Okay, because so it would be the other side. If the story would be the other side, if it was the other way, right? So here you reach the toppling P value first. So that means it's going to topple. All right, guys. So I think this pretty much sums up the lesson. So we've done all the things you need to know, sliding and toppling. So you can now go for the papers confidently, right, guys? So we'll see you in the papers.